So as the title suggests, I'm going to be talking about design innovation towards miniature near, I added the word near there, GPS quality clocks. So we're in the process of developing these miniature clocks with the goal towards getting them near GPS quality. And I'm going to be telling you about some of the trades we've had to make and some of the design innovations we've had to bring to get to the point where we are. So just a quick word on why we should work on this, though Greg also highlighted this in his presentation. And I took an excerpt from GPS World that did an article about a year ago on the economic benefits of GPS, both for its use as timing and also position. And this article says that there's about $56 billion in the US of economic benefit because of GPS. Goes on to say that GPS plays a critical role in 14 of 16 industries classified as US critical infrastructure. So you hear this at the same time that you hear questions about the vulnerabilities of GPS, the reliabilities of GPS, and the availabilities of GPS. So one of the motivations for this work is to mitigate concerns about the GPS availability and put new emphasis on technology development for improved self-contained timing solutions with near GPS performance that can operate in an environmentally rugged, rugged environmentally and low swap and also low cost. And the cost piece shouldn't be overlooked. Right now, the people who are enjoying these benefits of GPS timing are probably doing it with very low cost. They might not even know that they're getting GPS timing from their receiver and their antenna. So if they're going to switch to this solution, they have to have a low-cost solution. So in this audience, I don't think I have to go through how this clock is developed, but essentially it's a microwave frequency standard, or a microwave clock that operates in the ground state of a rubidium atom. Specifically, we use laser-cooled rubidium atoms, and because we don't have room to make a fountain clock, we just drop the atoms and then do time-domain Ramsey spectroscopy to measure the clock transition. So this is clearly proven physics, but the implementation in the miniature system is the challenge. So I'll just go through some of the design challenges that we've tackled, and this is by no means an exhaustive list, but some that I thought the audience might enjoy. So for light sources, as you've seen in a couple other, or maybe in your own labs, we tend to make these experiments with basically one light source or one light wave per every use that it might have in the clock. But the name of the game when you're trying to make this miniaturized is you have to minimize the number of lasers. This is important to reduce the power consumption, also important to reduce the cost. Yet we don't get away without having this requirement for high frequency agility. And we don't have the luxury of using acousto-optic modulators. They're too costly, have high insertion loss, have high power consumption. So the high frequency agility has to become inherent to the light source. And then as mentioned already in this session, we have to have high attenuation to reduce differential light shifts on the measurement. For the vacuum cell, since we're doing laser-cooled atoms, clearly this has to be compatible with ultra-high vacuum. Also, a very important note is that when designing this vacuum cell, you take into account, even though you want a small volume, you have to find a small volume that maximizes the beams that are used for laser cooling. And the NIST group has done a lot of work on characterizing how the number of atoms in the MOT scales with beam diameter, even as you go to very small beams. Also important is to minimize the amount of scattered light. As you start to get all these systems very compact and everything is happening in the same area, scattered light makes it more difficult to look at your signal. And so care has to be taken in the design of these to make sure you're minimizing scattered light. And then have a design that's compatible with your microwave cavity or microwave, the way that the microwaves are coupled into the atoms. For vacuum, I'm not going to talk about this today, but clearly there's a need to maintain ultra-high vacuum with long lifetimes, maybe 5 to 10 years. The kind of sizes we're talking about, you can't use commercial pumps, although there are efforts, research efforts ongoing to try to make pumps that would be adequate size for this application. Rubidium source, since we are loading our atoms from a background vapor of rubidium atoms, we have to have a way to maintain that ideal vacuum or background rubidium vapor over a broad temperature range. So if you're going to be operating maybe minus 40 to 100 degrees C, you have to be able to maintain that rubidium vapor pressure. And then microwave cavity, we need a low swap, size, weight, and power method for coupling the microwaves into the atoms that don't cause Doppler shifts or phase inhomogeneities. So not to belabor too much the point on the light sources, but what's really made this hard is that you have to have a high degree of agility. For each step in this process, there's a different configuration that's needed for the detuning of one or the other MOT or repumper beams and intensity control. So you have to meet all these agility requirements to optimize this system. We looked at two different configurations. One was a single laser that was locked to a rubidium cell, but had an etalon on board that was used to help us find those off-resonant lock points that we needed. And then we also worked with a miniature heterodyne module. So this is two lasers. The master laser is locked to a rubidium cell. It has a slave laser that's offset frequency locked from the master, and then you can tune that offset frequency to accomplish the agility. So while clearly a single laser approach is attractive from a power and cost perspective, we had issues with maintaining the reliability and the stability of it over many shots. Again, if you want to run this for 10 years at a rate of 50, several times a second, even, you can do the math on how many times this has to operate without error. We got much better luck with the miniature Heterodyne module in terms of its stability and reliability. We took some clock data with it, so this is the Allen deviation, and three different plots are shown here. The green is with our tabletop COTS laser for this particular clock that we made, and then the red is the miniature Heterodyne, so immediately you say, uh-oh, this is big offset, about a factor of 10, worse performance with the miniature Heterodyne. But one of the big differences between these two was the output power. The miniature Heterodyne was a little bit power starved because of issues with loss through optical isolators. If we changed our COTS laser to have equivalent power, the two stability curves almost overlap. So we think we can account for any performance impact from the miniature Heterodyne laser, but there's more work to be done here. I'll now go on to the vacuum cells. So I've listed again the challenges up here. Our basic approach was to machine glass blocks with the holes cut in them that would be where we would insert the beam paths. And then the geometry for the optical alignment was really set by the outer faces of the block. And then we would frit custom-coated optics on the block. So this is a picture of a block with custom-coated optics on it, so maybe mirrors or windows. And then we'd also attach these tubes, which were used to attach to the pump-out station, and also could hold our rubidium source. So we made several different iterations as we progressed through the phases of our development. The first two designs used what I call a folded retroreflected design. So we would put two input light waves, and then due to the configuration of the block, it would orient the beam so that we got the six lasers for, the 6 beams for laser cooling. We made an 18 cc version and an 8 cc version. Then we switched gears in the third phase of our development to go to a 1-1-1 configuration, so all the beams go into the top of the cell and then are retroreflected at the bottom. This reduced the part count down to only 3 parts that are fritted together, versus this was about 12 maybe. And we got down to 2 cc size for this block. You can see them now nested then in the coils and other steering optics that make up the magneto-optical trap. And we didn't do as much work to miniaturize all that, though I think by most standards it's still pretty small. There's a long ways to go, and we have some approaches to even miniaturize that further. Now, in regards to the rubidium source, again, what's the trick here is that we trap our atoms from a background rubidium vapor. And I think everyone in the audience knows that there's a strong scaling of vapor pressure as a function of temperature. And we're kind of lucky that at room temperature is about the right amount of vapor pressure in rubidium to do good magneto-optical traps. So this all works pretty well at room temperature. But if we're going to deploy this, this really has to work over a wider range of temperature. So maybe -40 to 80 C or -40 to 100 C. So if you have this big swath of temperature, you're going to be varying the vapor pressure density by 6 orders of magnitude, and it's just absolutely not going to work. So there's a couple ways that we could get at this problem, but the way we've chosen to solve it is, or attempting to solve it, is to try to create an ideal source that makes the right vapor pressure, but at your highest operating temperature. So basically set it at 100 C and then have that always make the right vapor pressure. And there's well-defined engineering techniques for making low-power thermal isolation chambers. So we need to invent this. This hasn't, nothing like this exists. The path we're going right now is called Rubidium intercalate sources. And so this was work that we picked up on that was actually done heavily in the 1970s for the lithium-ion battery community. And the whole point of this is to use highly ordered graphene, or graphite, excuse me, HOPG graphite. And as you synthesize these graphite and rubidium compounds, depending on the parameters of the synthesis, it tends to grow in very ordered stages. So a stage 1 would have layers of carbon and rubidium alternating. Stage 2 would have a rubidium, then 2 carbons, then rubidium, and stage 3 would be 3 interlaying areas of layers of carbon before you have rubidium. And though very little of this work in the 1970s was done for alkali atoms, we were able to get some of the thermodynamic properties, though at higher temperatures than we planned to use it. We were able to calculate what we thought the vapor pressures would be for this system at these different stages. And you can see that as you change the stage, you would get a different vapor pressure at different operating temperatures. So this seems like a good path to go down. So we generated a stage 1 intercalate shown here, and we measured its vapor pressure as a function of temperature, and we indeed found that it was about an order of magnitude lower than pure rubidium. This is not what our theory predicted, that we actually should have been several orders of magnitude away, but qualitatively it's correct. We also held the rubidium intercalate temperature constant and then swept the temperature, the ambient temperature of our cell, and the rubidium vapor pressure from the intercalate stayed constant, whereas, you know, if we had pure rubidium in there, that would change with the ambient temperature. We've also generated different stages, so stage 1, stage 2, stage 3, and for each one of those stages, we applied the amount of heat that was needed to make a vapor pressure of 1 × -7 torr. And this basically follows, again, qualitatively what our theory predicted, that as you go to stage 1, stage 2, stage 3, it takes more heat to generate that 10 to the -7 torr. So our operating parameter, we'd probably want to have a stage 2 intercalate that gives us 10 to the -7 torr at about 100 degrees C. And this is just to say that, again, none of our models quantitatively predicted, probably based on the fact that a lot of the models were taken at a temperature range that we're not operating in. I'll say a little bit about the microwave cavity, though I probably am using that word a little too loosely. So one of the issues with these small clocks is how do you effectively couple the microwaves into the atoms? And what you want to avoid is spatially varying microwave fields, because any spatial variation in the microwave field will be indistinguishable from a clock shift. So as I drop my sample of atoms, if they experience multiple phases, that will be a phase between let's say the top and the bottom. That will be a frequency shift or a clock bias. What's worse is if I have shot-to-shot variations in where the atom cloud ends up, either due to instabilities maybe in my optical beams or motion platform motion, then I'll have instabilities in that clock shift. So throughout the course of our development effort, we tried very hard to find the smallest size of, again, I'm using loosely the word cavity, the smallest size of device that could couple these microwaves into the atoms. Some of these made sense, some of them didn't. Oftentimes in these programs, you find yourself in a situation where you can't go back, you have to design around what you have, and that was certainly the case in some of these designs. We also were characterizing, we used a technique to characterize for these different configurations, characterize the frequency shift per millimeter, and over the course of these iterations got down to something that's about 0.002 hertz per millimeter shift. So just to give a little bit of the clock stability data, this is our phase 2 of development, and this was our measured Allen deviation or measured stability. And this data doesn't show it, but it was a pretty strong tail off, about 5e to the -13 for the fractional frequency stability. In this case, we were using this configuration. This was one of the folded retroreflected designs, and we were running up against a deadline, so we didn't have time to go redesign this. We had to squeeze in this loop gap resonator around it, And so it was a very funny shape, but it did get us some improvements in stability over what we'd had before. And then in phase 3, we had an opportunity to step back and redesign our vacuum cell and the resonator to go around it so that it was more symmetrical. And with that, we've remeasured the stability, and we're getting down below the floor that we saw in phase 2. We think this was the limiting error, down to about 2 to the minus 13, and still integrating down, so we actually don't know where the noise floor is yet with this configuration. In terms of G sensitivity, that's one thing that people worry about this. Certainly as an applications person, I worry about this because you can't flip over the clock and have it give you a different answer. It wasn't until phase 3 in our experiment that we had the ability to actually flip over our clock, but we could infer in phase 2 what would happen if we had flipped over our clock, and we would have seen clock shifts on the order of 2 to the minus 10. In phase 3, we actually did the measurement, flipped the clock over, and measured clock shifts of 1 to the minus 12, and we think we could do better than that. We could think we can do about another order of magnitude better. So with that, I will conclude to say that we continue to investigate the challenges of reducing the size, weight, and power and the fieldability for these higher performance clocks, hopefully approaching GPS-like performance. This is all known physics, but the challenges are in making the clock work with the size and power restrictions, and don't forget about the cost. So there's many trades that have been explored. We haven't seen any showstoppers, and we think there's a path towards greater miniaturization and power reduction with performance edging closer towards GPS performance. Thank you.